So in this video I'm going to go through an example just involving basic energy conservation, a problem that just uses conservation of energy dealing with kinetic energy and gravitational potential energy. No friction, no work, no springs, nothing with non-conservative forces or anything like that. That will be for some time later. So here we go. This is a problem that is from your textbook, and I wanted to go through the entire process just so that you see what is expected in terms of showing your work and how to apply the process of conservation of energy. So here we have the problem. Christine runs forward with her sled at 2 meters per second. She hops onto the sled at the top of a 5-meter high, very slippery slope. Very slippery means no friction. Question is, what is her speed at the bottom of the slope? Now, since there is no friction in this problem, it does not matter what path Christine takes to get to the bottom of the slope. If there was some sort of curve that she was constrained to go down the slope on, like let's say the sled was tied to something, but otherwise there was no friction other than just to help redirect the sled along that curve, she would still have the same speed at the bottom of the slope. Different paths would take different amounts of time, but by the time she reaches the bottom of the slope, she would still have the same speed. That's the power of conservation of energy when we have conservative forces, in other words, forces that conserve energy, in other words, things that are not like friction. And obviously friction actually does conserve energy, it's just that some of that energy becomes energy that isn't really useful for doing anything. In other words, heat is not really useful for going back into the system to allow Christine to get to the bottom of the slope at the same speed as she otherwise would without it. So anyway, as always, first we will write our givens. Her initial height, initial speed, and final height is 0. We're wondering what the final speed is. And we're going to write our conservation of energy statement, showing us and everybody else who's looking at the problem that we are using conservation of energy. Now, you can either write it like this, or you can add a plus W after this expression, or maybe W plus this, just so that people don't think that you're talking about a sum of works or anything like that. Work is energy that is added to the system or taken away from the system in some way. In this case, the work is 0. So a lot of people prefer to do the plus W no matter what, just because that is the real equation that's going on. But if you know that the work is 0, it's okay to get rid of that plus W in those ideal world situations where you know that there isn't any energy being added to or taken away from the system. So we're going to start with this, and then it's like, well, what does this mean? What is the sum of energy initially, and what is the sum of energy finally? Well, to figure that out, we draw an energy bar graph. Energy bar graphs are extremely important conceptual tools that allow us to visualize what's going on in these conservation of energy problems. And here it is for this problem. Initially, she has some kinetic energy, and she has some gravitational potential energy. And notice there's a G subscript right here to denote that this is gravitational potential energy as opposed to some other kind of potential energy like elastic potential energy. And at the end, it's all kinetic energy. In other words, she's at the bottom of the cliff, so there aren't any other potential energies going on here. So now let's see what this turns into. We have our sum of initial energy becomes kinetic initial plus gravitational potential initially. And our sum of final energy, well, there's only kinetic energy at the end, so that's just K sub F. The potential energy due to gravity at the end is 0. So we could have just crossed that out, but we decided to call it a 0. So what's left? Well, plug in the expressions for each of these terms. You must memorize that the formula for kinetic energy is 1/2 mv squared. It's also p squared over 2m, where p is the momentum, but that's something that is not important in this particular problem. What's important here is, well, we've been given the mass and velocity. Actually, we haven't been given the mass. Hopefully it goes away. Well, we were given the velocity, so we want the kinetic energy in terms of velocity. So we have 1/2 mv squared initially, plus gravitational potential energy initially. That's mgh. So you also need to memorize that the equation for gravitational potential energy is mgh. And you also need to understand the conditions under which that's true. This equation is not always true. It's only true if the acceleration due to gravity, little g, is basically unchanging during the motion. In other words, we don't have some sort of elliptical orbit or anything like that. In other words, as long as we're reasonably close to the surface of Earth, then little g is constant. As long as little g is constant, we can use mgh. We'll derive the more general situation where little g is not constant in Chapter 13. But anyway, finally for kinetic energy final, we plug in 1/2 mv final squared. And after all, remember that v final is what we're really after here. That's our unknown. And lo and behold, each of these expressions has a mass m to the first power in it. You can divide both sides by m and it's going to go away. And you can also multiply both sides by 2. That makes it a little easier to solve. And then take the square root of both sides. And now we're ready to plug in numbers. There we go. And now we get Christine's final velocity or final speed at the bottom of the cliff, 10.1 meters per second. So that's the use of conservation of energy to solve a basic problem where we never needed to draw any free body diagrams in terms of figuring out what kind of forces are acting in here. This is simply a before and after scenario. So this makes those types of problems a lot easier as long as there's no friction. Even when there is friction, though, we have a way for dealing with that, and that's what we'll get to later on. Thank you.